Okay, so today we're going to start the section on antiderivatives, and this is actually pretty much giving us a glimpse as to what to expect second semester. So first semester, our main focus were on derivatives, and we use derivatives to do a bunch of, to answer a bunch of different types of questions. So in this section, we're kind of going to talk about antiderivatives, and then later on in the semester, we're going to figure out, hey, look, antiderivatives do a bunch of things. um, we can use them to apply to a bunch of other conceptual ideas. So let's define what an antiderivative is. And you should be fairly familiar with antiderivatives. It's kind of like we're working backwards as to what we did first semester. So here's how we define it. We could say a function, and let's call it capital F, is called an antiderivative of another function, let's call it lowercase f, on some interval I if I take the derivative of capital F and I get lowercase f. So basically, what do we know? I would call capital F the antiderivative of lowercase f if the derivative of capital F gives me lowercase f, which kind of, as you could notice, it's working backwards, right? In first semester, we found derivatives, so we could find the derivative of lowercase f. Second semester, now we're going to work backwards. We want to find an antiderivative of this guy, which would be capital F. And how do I verify that this is the antiderivative of that? Well, if this is truly the antiderivative of lowercase f, then if I have to find the derivative of capital F, that will take me back to lowercase f. So this is for all x in this interval. So basically, whatever that interval is, capital F prime should give me lowercase f. Okay, so before we do a bunch of examples, and then that'll pretty much end the section. So today's section is fairly low, and we're dividing into 2 days anyway. Let's talk about this theorem, our first theorem. So this theorem says the following. If f is an antiderivative so if it's an antiderivative of lowercase f on an interval I, then the most general antiderivative of f on that interval is capital F of x plus c, where c is arbitrary. So basically what this theorem is saying is, look, if I give you lowercase f and I say find the antiderivative of this and you call it capital F, you always have to understand that when we find the antiderivative of a function, we always have to put a plus c. Okay. Now there will be instances where we'll be able to figure out what this constant is exactly, but here's the problem. See, why do we need to put this plus c? Think of it this way. If I said, and let's come up with a very simple example. If I said find the antiderivative of f of x equals to 2x, okay? And see, this is something simple. You could find the antiderivative of this. You could say, what must have this function been before this, where when I took the derivative, I got 2x? You would say f of x is equal to x squared. But here's the problem. If you say it's f of x equals to x squared, yes, that's true that the derivative of this gives me 2x, but then I could argue with you and say, but wait a minute, who said it has to be x squared? I was actually thinking of x squared plus 1, which notice how x squared plus 1, also the derivative of it is 2x. So to be safe, or to cover your bases, you're going to say, look, the antiderivative of this is x squared plus any constant. So then I can't argue with you and say, well, then I was thinking of x squared plus 5. You'd say, well, since I don't know what constant you're thinking of, I'm saying the antiderivative of 2x is x squared plus some constant. Now, why do we put the plus some constant? Is because we know when we find a derivative of this, the constant is going to go away. So in this class, anytime you find an antiderivative, you always have to put the plus c. Okay, now, sometimes we'll be able to figure out what this constant is, other times we won't. But if you don't put the plus c, you're going to be incorrect because you're being way too specific. See, if I were just to put x squared, then you're automatically assume that the c is 0. But who said the c is 0? It could be anything that it needs to be. So just keep that in mind, especially on quizzes and tests. When you find an antiderivative, you need to make sure that you put that plus c. Okay, so for the time being, the examples that we do is strictly going to rely on kind of the, are the shortcuts that we've learned of. Okay, so let's go through the first few examples. So example 1, we're going to say find the most general antiderivative of the following. So a, which is f of x, equals to 1 over x. B, which is f of x, equals to cosine of x. And C, f of x, which is equal to x to the power of n. And we're saying n does not equal to -1. Okay? So these are the 3 problems that I want you to work on. So why don't you pause the lecture, try to find these antiderivatives on your own, and then press play just so you could listen in on what's happening here. So now, to find the antiderivative of this, here's what I know. We know from semester 1 that the derivative of ln of x gives me 1 over x. However, when I find the antiderivative of this, I need to make sure that the antiderivative exists for all x values except for 0. So if you remember the antiderivative, or what we need to say is that the antiderivative of 1 over x is going to be ln of x. However, we know that the natural log of x cannot be, we can't have a negative in there. So we need to fix it so that it's defined for all values except for 0. So, I mean, one way of doing this, and I kind of like to think of it this way, and then we'll kind of put it together and make it more concise. But here's what we're going to say. We'd say that the antiderivative of 1 over x is going to be ln of x if x is greater than 0. So then what are we going to do if x is less than 0? The antiderivative of 1 over x will still be ln of x, except it'll be ln of negative x if x is less than 0. So what we notice here is that, oh, and I should not forget the plus c. I was just making a fuss over how the plus c is important. So here we go. We found our antiderivatives. And then now that we have this, we notice, wait a minute, this looks familiar to us because I could write this piecewise as a singular value, which is the same thing as ln of absolute value of x plus c. So basically what we're saying is, look, the antiderivative of 1 over x is always ln of absolute value of x plus c. Now, when could we drop the absolute value? If you're told that x is a positive number. But if you notice how this is defined everywhere except for 0, which clearly 1 over x is defined everywhere except for 0. So the antiderivative of 1 over x is ln of absolute value of x. Now, the reason why I wrote this is for you to see why it becomes absolute value of x, because remember, absolute values could be written as piecewises. So if I said, look, start with this and work backwards, you would write this as a piecewise, and this is what it would look like. Okay, so generally, books say the antiderivative of 1 over x is ln of absolute value of x. But if you're wondering where the absolute value is coming from, is because we need to make sure that these antiderivatives match the domain of 1 over x. Okay, so moving on. For cosine of x, what is it that we know? See, we're working backwards now. So the one thing that you have to remember, you have to think backwards. So we know that the derivative of cosine is negative sine, but the derivative of sine is cosine. So to get to cosine, the antiderivative of cosine would be sine of x plus c. You just need to make sure that you understand that whatever this is, when I find its derivative, I should get that back. Okay, so the one thing that you should remember or keep note of is when the derivatives are negative, it's kind of we're going in reverse. So when you find the antiderivatives, kind of things are in a reverse order. So the derivative of cosine would be negative sine, but the antiderivative of cosine would be sine. In other words, the antiderivative of sine would be negative cosine, and so on. Okay, so now let's look at this. With this one, here's what we know. We're assuming n is a positive number, and we're told that n isn't negative 1, because if n were negative 1, then it would give us this 1 over x, which would give us an ln graph, or an ln as my antiderivative. So to find the antiderivative of this, we're basically going to use the reverse of the power rule. So it'll be what? X to the power of n plus 1. So you remember when you use the power rule, what would you do? You'd bring the power down, and then you'd subtract 1 from this. Now we're, instead of subtracting 1, we're adding 1. But now look, how do I balance this n plus 1 out? The problem is this: when I find the derivative of this, I need to make sure that I get 1 x to the power of n, which means if I add 1 to the power, I need to put a 1 over n plus 1 in front of it, because when I find the derivative of this, I want this to become a 1. So notice how if I bring the n plus 1 down, the n plus 1s will cancel out and we'll get that. So if I hadn't put this here, what would be the problem? When you find the derivative of this, you'd get n plus 1 times x to the power of n, which notice, however, here I don't have an n plus 1, so I need to kind of adjust for this to make sure that when I find its derivative, I get back to this. So then I would also have to put a plus c. Okay, so there you have it. We did an example where we kind of worked through these, and if you think about it, I used the shortcuts that we learned from semester 1 to work with these. Okay, so moving on to example 2. We would say find f if f prime of x equals to e to the x plus 20 times 1 plus x squared to the negative 1. And we're told that f of 0 equals to negative 2. So now let's kind of focus on this for a minute. And if you want, you could try to find this on your own and then press play on the lecture. First pause it and then play it again to see if you got this right. But here's what I know. We have f prime. We're trying to find f. Well, clearly f is the antiderivative of f prime. Now, to look at this here, what is this going to do? Well, this guy I don't care about right now, okay, because what I need to do is I need to grab this guy and I need to find its antiderivative, and then this will actually help us find our constant. So I'm not worried about this yet. First, let's find the antiderivative, and then we will use this to help us find c. So now, if I start off with f prime of x, which is e to the x plus 20 times 1 plus x squared to the negative 1. Now, see, this one we already know what its antiderivative would be. But this guy, I don't know what its antiderivative would be just yet, or it looks a little more complicated. So what I could do is we could say, look, we could rewrite this as e to the x plus 20 times 1 over 1 plus x squared. Now, hopefully, this antiderivative looks familiar for you guys, which this would be, what is this? This is the derivative of actually tangent inverse. So the antiderivative of this would be tangent inverse. Now remember, constants we don't care about. They kind of just tag along. So it's kind of like the same idea. So when I have it written like this, I could now say, look, f of x would be, the antiderivative of e to the x is e to the x plus 20 times the antiderivative of 1 plus x squared, 1 over 1 plus x squared is tangent inverse of x plus some constant. Okay, so there you have it. Now, given that f of 0 is negative 2, I could solve for c. So that's where this helps us find this constant. So now I could specifically find out what that constant is. So what do I need to do? Replace y with negative 2 and x with 0, and then that allows us to solve for c. So I have negative 2 equals e to the 0 plus 20 tangent inverse of 0 plus c. So what do I know? I get negative 2 equals e to the 0 is 1 plus 20 times tangent inverse of 0 is actually 0 itself. So what do I get? Negative 2 equals 1 plus c, which this implies c equals to negative 3. So then my final answer is f of x equals to e to the x plus 20 tangent inverse of x minus 3. Okay, and there you have it. So the last example I want to do is another one. And so I think this one you should have more confidence in yourself, so you should be able to do this on your own. So find f if f double prime of x equals to 12x squared plus 6x minus 4, with f of 0 equals to 4 and f of 1 equals to 1. So once again, you can guess that this fact I don't care about until the end anyway, because these are going to help me find my constants. So look at what I've given now. Now we have the second derivative, and we're trying to find f, which this is fine, because what does that mean? To find f, I would just need to find the antiderivative of this, which would give me f prime. And then when I get f prime, I would need to find the antiderivative of that, which would help me get to f. So, and if you notice this, this is just kind of like the power rule in reverse. So we could see that if f double prime of x is 12x squared plus 6x minus 4. What does that mean? F prime of x would be, this is what? This will be an x cubed. And what do I need to do? What does this number need to be? Well, it needs to be a number where if I were to find its derivative, I would get 12, which would have to be a 4. Because look, find the derivative of this, 3 times 4 would give me the 12. So then this would be what? X squared, and then the number in front would now be a 3. And then this would be a minus 4x plus c. Okay, so here's f prime. So let's not worry about c yet, because I can't find c because I don't have any information about f prime. But I have enough information to help me find c once I know what f is. So let's go through this. Now, if f prime is this, f of x is the antiderivative of this. So what would that be? It would be x to the 4th, and the nice thing is the number here would just be a 1, because to get 4 out of it, I would just find a derivative and I would get the 4. Plus, same thing goes here. This would just be x cubed, okay, because the derivative of x cubed is 3x squared. This would be what? Minus 2x squared. And then this would be plus cx plus d. So notice how I have two constants to solve for. Now it makes sense to us why, and by the way, this is a c and this is a d. So sometimes it looks weird. It looks like I'm writing parentheses here. But here's the thing. To find c and d, I would need 2 points on this curve. And we could see now we have why we have 2 curves. So what do I know? If I plug in 0 for x, y should be 4. So let's do that. So 4 equals 2. If I plug in 0, this becomes 0, 0, 0, 0, and I just get d. So that helped me find d right away. So that means f of x equals to x to the 4th plus x cubed minus 2x squared plus cx plus 4. Now to find c, I'm going to use this fact. When x is 1, y is 1. So do the same thing. If I plug in 1 for y and 1 for x, what do I get? I get 1 here, plus another 1, I think I'm running out of ink here, plus another 1, minus 2 times 1, which is 2, and then this would be what? Plus c plus 4. So now we could simplify here and solve for c. So what do I get here? 1 plus 1 is 2, minus 2, that's gone, plus 4, so subtract 4 from both sides, and I get negative 3 equals to c. So my final function, f of x, will be x to the 4th plus x cubed minus 2x squared minus 3x plus 4. And here's f of x. Okay, so like I said, the antiderivative is, we're literally working backwards as to what we were doing semester 1. Okay, so that basically wraps up the first part of the notes for section 10. We'll continue on with the notes tomorrow. Okay, but we don't have much left. So this pretty much wraps things up for today.